Welcome to massive open online course on basic principles and calculations in chemical engineering. So, we are discussing about basic principles of multiphase systems under module 5. Now, in this module we will discuss about the equilibrium laws, humidity and saturation. In the previous lecture we have described regarding that phase equilibrium, and there are different laws, and also in phase diagram how we can read the different state of the substances at different temperature and pressure, and how that phase rule is applied to specify the variables of the systems to identify any properties of the system. And also we have described the vapor pressure of the equilibrium condition, and also how that vapor pressure can be calculated by Clausius-Clapeyron equation, even with other equation like Antonis equation, and from the Cox's chart how it can be used to calculate that we have discussed there. In this lecture we will try to describe more about that equilibrium conditions of the systems, and how also that partial pressure and vapor pressure they are related with that liquid phase composition and vapor phase composition at its equilibrium condition with this partial pressure. And also we will try to describe something about that humidity and saturation, how that humidity criteria, even what is the can say that moisture that is present in the atmosphere or in dry air, how it can be calculated from a that psychometric chart that we will try to learn something here in this lecture. Now, as we are talking about that multiphase systems, of course that in many chemical and biochemical that process systems, you will see that more than one phase will be involving for different chemical engineering process to procure, or you can say to get the different products based on that processing of that multiphase systems. Now, in that case you will see that those phases may be sometimes in a particular condition at a certain temperature and pressure, they will be in equilibrium, what we have described in our previous lecture. And also we have described that what are the different equilibrium condition like equilibrium constant, solubility equilibrium, thermodynamic equilibrium, vapor liquid equilibrium, and based on that vapor liquid equilibrium how vapor pressure will be changing at that particular temperature, and also how that partial pressure or molar composition can be calculated based on that that system pressure and also vapor pressure there. Now, we have that discuss about that Clausius-Clapeyron equation to calculate the vapor pressure, and at different temperature if you know the can say that vapor pressure of the systems, then you will be able to calculate what should be the latent heat of vaporization, or if you know the latent heat of vaporization and at a particular temperature what should be the vapor pressure of the substance, then based on that quantity you will be able to calculate what should be the vapor pressure of other temperature for that particular substance based on this Clausius-Clapeyron equation. Now, here in this case we will discuss another law that is called Raoult's law, which actually will give you the characteristics behavior of the ideal solution. What is that ideal solution? It will be generally regarded as the mixture of components in a solution whose properties can be calculated based on the knowledge of the corresponding properties of the pure components and the composition of the solution. Now, in this case this Raoult's law will be applied when the mole fraction in the liquid phase that will approaches unity, and or for solutions for very similar in chemical nature. Now, in this case this law actually relates the partial pressure with the mole fraction in the liquid phase. Suppose there is a substance like liquid is becoming its vapor at its particular equilibrium condition. or you will see that in a particular solution you will see that some components will be there, and whenever it will be vaporizing, some components will be going to the vapor phase and some components will be remaining in the liquid phase. Now, what should be the component of that what should be the concentration or mole fraction, or you can say mass fraction in the liquid solution at a certain temperature and also pressure, based on which you will be able to calculate that what should be the partial pressure there, and also what should be the vapor pressure at its equilibrium condition, that partial pressure also will be related to that. So, you know that this Raoult's law it generally relates the partial pressure with that mole fraction in the liquid phase. Here we can say that here this partial pressure will be equal to mole fraction into system total pressure, and this partial pressure again it will be related to the what will be the mole fraction of that components in the liquid phase, that is denoted by xi, and what should be the vapor pressure of that components at that particular temperature. So, if you know the that mole fraction of that particular component in the liquid phase and the vapor pressure of that component at that particular temperature, then the partial pressure of the that liquid phase will be, or vapor phase partial pressure of that component that will be related to this that mole fraction of that component in the liquid phase and vapor pressure of the component at that particular temperature. So, this equation given in these slides is basically the mathematical expression for this Raoult's law. So, this is basically a relation between that partial pressure and the mole fraction of the component in the liquid phase and vapor pressure. So, here Pi is the total pressure and P is the total pressure and Pi is the partial pressure of the species I, and PIV is the vapor pressure of the species I at temperature T. And you will see that the law applies only to mixture in which components are chemically very similar, and the mole fraction of the components that will do not interact in any way. So, based on this criteria, this Raoult's law will be applied. So, here we can say that by this Raoult's law we will be able to know what should be the partial pressure at a particular temperature. Once you know the mole fraction in the by equilibrium condition of that components and also system pressure, then you will be able to calculate what should be the partial pressure. And also you can calculate that vapor pressure if you know the partial pressure and you know the mole fraction of the components in the liquid phase, then you can also calculate what should be the vapor pressure there. Again you can calculate the mole fraction of the liquid phase if you know the partial pressure and the vapor pressure there. So, based on this Raoult's law and based on this equation you will be able to calculate either partial pressure or vapor pressure or mole fraction of the components in the liquid phase. Now, let us do an example here. Now, what is the change in vapor pressure when 164 gram of glycerin is added to 338 milliliter of water at 39.8 degrees Celsius. In this case the vapor pressure of the pure water at 39.8 degrees Celsius is 54.74 torr, and the density of the water at this 39.8 degrees Celsius is given as 0.992 gram per milliliter. So, at this condition you have to calculate what should be the change in vapor pressure of this amount of glycerin when it is added added to this 338 milliliter of water at 39.8 degrees Celsius. Now, in this case first of all you have to calculate what should be the mole of that glycerin here. So, this glycerin mole of glycerin can be calculated just by amount of that glycerin added divided by its molecular weight. So, simply you can get this mole of glycerin will be equal to 1.78 mole, and also what will be the volume of water, it is given, that is 338 milliliter of water, and this 338 milliliter of water that means here how many moles of water will be there, that will be just simply 18.63 mole, just by having that 1 mole of components will at particular temperature and pressure, that is at normal temperature and pressure, will give you that 22.4 liter. So, according to that we can say that how many moles of this water will be there simply, and after that you have to calculate what should be the mole fraction of water in the solution of that glycerin. So, mole fraction of water, if you know that mole of this individual component of glycerin and also water, then mole fraction will be equal to what? That means here moles of water divided by total moles of mixture, that is moles of water and moles of glycerin. So, in this way we can say that a mole fraction of water will be equal to 0.91 according to this calculation. And then we know as per Raoult's law that partial pressure of the components will be equal to mole fraction in the water into partial pressure of water will be equal to mole fraction of water into vapor pressure of water. So, according to that we can calculate what will be the partial pressure of water, it will be equal to x water is 0.91 and vapor pressure is 54.74, it is given here. So, ultimately it is coming 49.8 torr. Now, in this case you will see that the change in pressure will be as what is the final pressure of that water, and also what will be the initial pressure of that water vapor. So, here in this case final that pressure is coming as what is that P final here as that water partial pressure at that particular condition, then it is coming 49.8, whereas vapor pressure is at that particular temperature is 54.74 torr. So, if you subtract this you will get that change in vapor pressure when if you are adding this glycerin of this amount. So, it will be coming as minus 4.94 torr. If we consider a binary mixture for that Raoult's law, what will happen? Suppose there is a mixture of components A and B. So, partial pressure of component A can be represented by Ya into P. Ya is the mole fraction of A, and that will be equal to Xa into PAV. X is the mole fraction of component A in the liquid, and PAV is the vapor pressure of the component. Similarly, for component B, that partial pressure of the component B will be equal to Yb into P, and that will be equal to what? Xb into Pb V. That means here mole fraction of component B into partial pressure of component B. Since we know that for binary mixture that is Xa plus Xb that will be equal to 1, that means summation of mole fraction of components will be equals to 1. So, here Xa plus Xb will be equals to 1, that implies that Xb will be equal to 1 minus Xa. So, if you substitute here 1 minus x instead of xb, then you can simply write here that 1 minus x into Pbb. So, that is why this Pb, that means partial pressure of the component B, will be equal to 1 minus x into Pbb. Now, from Dalton's law that we have discussed in our earlier lecture, that Dalton's law basically says that the summation of partial pressures will give you the total system pressure. So, here in this case total pressure will be equal to summation of this partial pressure of component A and B. Then we can substitute that value of Pa and Pb here, then we can write like this Xa into Pab plus 1 minus x into Pbb. So, from this we can express here what should be the mole fraction of A, that mole fraction of A can be calculated as Pa by P. So, this will be simply that Xa that Pa B by P. So, P can be calculated from this equation, and then mole fraction of P's component can be calculated by this equation. Once you know the vapor pressure of P's component and also mole fraction of component A in the liquid and also total pressure, then easily you can calculate what should be the mole fraction of A. Similarly, mole fraction of B in the vapor phase, or that is you can say that at equilibrium condition in the vapor phase, then Yb that will be equal to here 1 minus Ya. So, in this way you can calculate what should be the mole fraction of B there. Let us do an example based on these principles. Now, it is told you to that estimate the vapor phase composition at 0 degree Celsius in equilibrium with a liquid mixture that contains 40 mole percent of benzene and 60 mole percent of toluene. Also, you have to calculate the composition of the liquid mixture which boils at 90 degree Celsius and 760 torr, and vapor pressure data is given to you. At 60 degree Celsius, this vapor pressure of benzene is given 385, whereas vapor pressure of toluene is given 140 there at that 60 degree Celsius, and at 90 degree Celsius this vapor pressure of benzene is 1013 and vapor pressure of toluene is 408 torr. Now, if you apply the Raoult's law to solve this problem, we can write here what should be the partial pressure of benzene, that is based on that Raoult's law we can write X benzene into that partial pressure of benzene, vapor pressure of benzene. So, partial pressure of benzene, that will be equal to mole fraction of benzene to vapor pressure of benzene, that will be equal to what here 0.4 into 385. What is that 0.4? It is given that 40% of benzene will be in the mixture, and vapor pressure of benzene is given as 385. So, if you substitute this value and then multiply it, you will get this 154 torr of that benzene. So, similarly, for toluene, that partial pressure will be equal to mole fraction of toluene into vapor pressure of toluene. So, if you substitute that mole fraction of toluene, that is 0.6, and vapor pressure of toluene, that is 140, after that if you multiply you will get that 84. Now, from this you can calculate what should be the total pressure. That total pressure will be equal to summation of that partial pressure of those components here. So, it will be coming as 154 plus 84, then it will give you that 238 torr. Now, you have to calculate what should be the vapor phase composition at 60 degree Celsius. So, here vapor phase composition will be at that 60 degree Celsius, that can be represented as Y benzene, that will be equal to P benzene, partial pressure of benzene out of total that pressure. Then we can substitute this partial pressure of benzene, which is equal to 154, and this total pressure is 238. So, it will be coming as 0.648. Whereas, the same way we can calculate that toluene mole fraction, and that can be expressed as ratio of that partial pressure of toluene to the total pressure of the system. So, it will be coming as 84 divided by 238, then it will give you 0.352. So, these are the mole fraction of benzene and toluene in the vapor phase. Now, next problem is that you have to find out the liquid phase composition at 90 degree Celsius. Now, in this case again you have to calculate what should be the total pressure at that 90 degree Celsius. Now, again that total pressure will be equal to that partial pressure of benzene and partial pressure of toluene. Now, that partial pressure of benzene as per Raoult's law can be expressed as X benzene into vapor pressure of that benzene. Similarly, for toluene, that is 1 minus benzene into vapor pressure of toluene. So, after substitution of that composition benzene and toluene, we can obtain that that total pressure there. But here since that total pressure is not changing, so we can write here this that 760 as given here. So, this 760 and also partial pressure as per that, this what should be the vapor pressure there also it is given. So, that vapor pressure if you substitute here and then composition of that benzene it is not known to you. So, finally, from this equation you can calculate what should be the mole fraction of benzene in the liquid at that particular temperature here as 90 degree Celsius. So, similarly, X toluene, that means mole fraction of toluene also you can calculate from this equation. So, it is coming finally that mole fraction of benzene is 58.2%, whereas mole fraction of toluene is coming here 41.8%. Now, we have discussed about that ideal solution where you can apply that Raoult's law, and if suppose any solution do not obey that Raoult's law at every range of concentration and at all temperatures, that will be called as non-ideal solutions. Now, non-ideal solutions actually deviate from that ideal solution in two ways, that is where that non-ideal solutions that will be showing positive deviation from the Raoult's law, it will be regarded as that positive deviated that non-ideal solution, and in this case the vapor pressure of the component will be greater than what is expected in Raoult's law, whereas some solutions will give you that negative deviation from that Raoult's law, and in that case the pressure that is vapor pressure will be less than what it actually should be for that system according to the Raoult's law. Now, some examples of that solutions that will be showing positive deviation from the Raoult's law, like here acetone and carbon disulfide mixture, acetone and benzene mixture, carbon tetrachloride and toluene or chloroform mixture, even methyl alcohol and water, acetone and ethanol mixture, ethanol and water mixture, that will be regarded as that non ideal solution of having positive deviation from Raoult's law. Similarly, some solutions will also showing negative deviation from the Raoult's law, like some examples here, the mixture of chloroform and benzene, mixture of chloroform and diether, mixture of acetone and aniline, mixture of nitric acid and water, and mixture of that acetic acid and pyridine, and also mixture of hydrochloric acid and water. So, this combination of this solution you can call that are non ideal solution, which will show you the negative deviation from the Raoult's law. Another important properties of this solution, it is called that relative volatility. You will see that this relative volatility of properties will measure the difference in volatility between two components and hence their boiling points, and in this case ratio of pure component vapor pressure will give you that that relative volatility, and it will be represented by that alpha AB. This alpha AB then will be defined as that, what is that? This is your what is that vapor pressure of that pure component, and A, and this is vapor pressure of component pure component B. So, this is your this vapor pressure. Why it is called vapor pressure? Because we know that from that Raoult's law that partial pressure that will be equal to that xi into that vapor pressure of that component. So, in this case we can write then vapor pressure of that component will be equal to simply that partial pressure by its mole fraction. So, from this we can say that for component A, that you can write that vapor pressure of component will be as Pa by Xa, and similarly for component B it will be equal to that Pb by Xb. So, this relative volatility will be defined as this ratio of this vapor pressure of component A to the vapor pressure of component B, and it is denoted by alpha AB. And this alpha AB also can be defined as this, what should be the mole fraction of component in the vapor phase to it in the liquid phase for the component A. Similarly, what should be the that ratio of the mole fraction of that component B in the vapor phase to the liquid phase. So, in this way also you can calculate that relative volatility. And if we that substitute that value of this y in terms of x, then you can finally calculate that what should be that form of equation of that mole fraction in the vapor phase in terms of that liquid phase mole fraction. So, this equation will give you that some equilibrium equation based on its relative volatility. Now, more volatile components, that is at normal boiling point degrees Celsius, and some will be some less boiling component normal boiling point, and their relative volatility here given as here. Suppose there is a mixture of benzene and toluene. Here in this case, more volatile component is benzene, whereas less boiling point component is toluene. In that case, this relative volatility will be equal to 2.34 as per that that condition. Similarly, for toluene and xylene mixture, this relative volatility is 2.31. Benzene and xylene mixture, it will give you 4.82. M xylene and P xylene, that is metaxylene and paraxylene mixture, it will give you that relative volatility will be equal to 1.02. Pentane and hexane, it will give you that relative volatility as 2.59, whereas the mixture of hexane and heptane will give you the relative volatility as 2.45. So, this you can calculate how to assess that the components, whether it will be volatile and how it will be relatively more volatile than other components there. Now, vapor liquid equilibrium curve also can be made based on that relative volatility and also composition of that mixture. Now, as we told that this here from this relative volatility relationship, we can form this equation y is equal to alpha ABE into x divided by 1 minus alpha ABE minus 1 into x. What is alpha ABE? This average volatility at the range of temperature, and also this x is the mole fraction in the liquid phase and y is the mole fraction in the vapor phase. Now, if we consider any components, then we can say that suppose A, so y A will be equal to alpha A B into that x A divided by 1 minus that alpha A B minus 1 into x A. So, similarly for a component A, we can represent this that y and x relationship in a graphical form. Like in that case, suppose if we consider that benzene, now mole fraction of benzene in the liquid can be represented as x and mole fraction of benzene in vapor as y. So, as per that equation of y is equal to alpha x by 1 minus alpha minus 1 into x, then we can get this. If you consider that mole fraction will be 0 to 1, and if you change that mole fraction of x in the liquid phase accordingly, then it will come as that y value. Here in this case, alpha AB value is given as per table here. Suppose if there is a benzene toluene mixture, then you have to consider that relative volatility will be equal to 2.34. So, if you write here alpha as 2.34, and if you change the value of x accordingly, you will get that y value. So, if you plot this, you will get that different values of that y value based on this different value of x. So, this line will be represented as that equilibrium line. This is equilibrium line. So, this equilibrium line will actually be calculated when and how actually that benzene will be relatively higher volatile or less volatile relative to that other component, and it will be useful for basically for distillation operation in chemical engineering process. So, in that case this that vapor liquid equilibrium curve to be generated, and also based on this vapor liquid equilibrium curve you will be able to assess what should be the different mole fraction of components in different temperature as well as at different stages, and also what should be the mole fraction in that liquid phase of that component at different temperature and at different stages of that distillation processes. Now, another important equilibrium law, it is called Henry's law. Here in this case this Henry's law will apply for dilute solutions of any compound like I here, that is xi, that almost will be equals to 0 because it is dilute. You can say that will relates that partial pressure in the gaseous phase with the mole fraction in the liquid phase, that is air dissolved in water like this. So, in that case this partial pressure of that component will be equal to that will be proportional to that that mole fraction in the liquid phase, and then proportionality constant will be regarded as Henry's law constant at that particular temperature, and it generally increases with increasing temperature, and you can say that if you have less values of Henry's constant, you can expect that solubility will be higher. At higher pressures or for gases of high solubility, the law actually will not actually valid. So, in that case this law loses its validity, and for ammonia in water at 20 degrees Celsius, in that case Henry's law constant will be equal to 2.7 atmosphere per mole fraction there. So, we can say that this for dilute solutions of any compound, in that case partial pressure will be related to again that mole fraction of components in the liquid phase, but this here the proportionality constant will be as Henry's law constant, and this Henry's law constant will give you whether this components will be soluble or not. Now, some Henry's constant for the solubility of some gases in water is given, like here some components are shown here in the slides, like hydrogen, nitrogen, carbon monoxide, oxygen, methane, even ethane, carbon dioxide, chlorine, hydrogen sulfide, and their respective that Henry's constants are given the slides at a different temperature, 0 degree Celsius and 25 degrees Celsius at constant pressure. So, in that case how this Henry's law constant will be varying with respect to temperature, it is shown, but you have to give special attention to that gases nitrogen and hydrogen. In that case both components Henry's constant decreases by a factor of about 3 as the temperature is increased from minus 25 degrees Celsius to 25 degrees Celsius. There may be unexpected result that the solubility of these gases in ammonia is higher at high temperature there. So, you have to see these changes of this Henry's law constant at this hydrogen and nitrogen gases. Now, let us do an example based on this Henry's law here. How many grams of carbon dioxide gas is dissolved in a 1 liter bottle of carbonated water if the manufacturer uses a pressure of 2.4 atmosphere in the bottling process at 25 degree Celsius. In this case, Henry's law of Henry's constant of carbon dioxide in water is given as 1.65 into 10 to the power 3 atmosphere by mole fraction at 25 degrees Celsius. Now, mole fraction of carbon dioxide dissolved in water, you have to first find out, that will be x CO2, that can be calculated based on that Henry's law. It will be coming as simply that what is the law here, this Pi is equal to x A into H, that means here x A will be equal to Pi by H, that means here P is here partial pressure of that carbon dioxide and here H is Henry's law constant. So, here partial pressure is given to you, that is 2.4 atmosphere, and Henry's law constant it is given 1.65 into 10 to the power 3, then finally it is coming as 0.001452. This is the mole fraction of carbon dioxide. Similarly, moles of carbon dioxide per moles of water, how it will be calculated. So, here moles of carbon dioxide divided by then moles of water. So, moles of water will be coming as 1 minus that is moles of carbon dioxide, then after calculation it is coming as 0.00145. Now, 1 liter of water, we can say that that 55.55 moles of water. This is in liter of water, then you have to calculate in terms of moles of water, because 1 mole of water is equivalent to 22.4 liter of water. So, based on that you can calculate what should be the moles of water in this 1 liter of water. Therefore, moles of carbon dioxide dissolved, that will be equal to what, because 1 moles of water will dissolve this mass of 0.00145 moles of carbon dioxide. So, if you have this this 55.55 moles of water, then you can easily calculate what should be the moles of carbon dioxide will be dissolved in the water, then it will be equal to 0.00145 into 55.55. So, this will give you that here 0.081 moles of carbon dioxide that will be dissolved in 1 liter of water. So, this moles of carbon dioxide simply it will give you 3.553 grams of carbon dioxide if you multiply it by its molecular weight. Now, then vapor liquid equilibrium ratio, another important properties of this gas liquid mixture at its equilibrium condition. In that case, the mole ratio of the component in the vapor to the liquid at equilibrium is called the vapor liquid equilibrium ratio, and it is also called that distribution coefficient, how moles will be distributed in the vapor from its liquid phase, and it can be mathematically expressed by this that Ki will be equal to Yi by Xi, whereas this Ki will be called as that equilibrium constant, or sometimes it is called distribution coefficient, and it is simply that what is the moles of that component in the vapor phase and moles of component in the liquid phase, and what is the ratio of these two. And if you substitute that if we apply that Raoult's law, then we can say that this will be basically as that ratio of vapor pressure to the total pressure of the system. Now, as per Dalton's law, we can have that partial pressure will be equal to Yi into P, or as per Raoult's law it will be Pi into Xi into PIV into T. That means here mole fraction of that component into vapor pressure of that component. So, according to that, if we substitute here, you can simply say that this Ki will be equal to here Pa, that will be a ratio of vapor pressure of the component to its total pressure. Now, saturation, what is saturation? You will see that the gas phase sometimes cannot accommodate at any more vapor from the liquid phase at a particular temperature and pressure. Now, any attempt in adding more vapor from the liquid phase, if you increase the partial pressure there, or you can say if you add more vapor there, there will be increase in partial pressure, that may lead to the condensation. Now, you will see that if you add more vapor from the liquid phase, and you will see that the partial pressure will keep on increasing there. So, when you will see at a condition when you will see that partial pressure will be almost will be equals to vapor pressure, you will see that solution will be saturated with that vapor component. So, we can say that at a saturation condition partial pressure will be equal to vapor pressure. So, we can say that temperature at this point of this saturation, where vapor phase is that tries to be condensate at that saturated temperature. So, that temperature will be called as dew point temperature. So, you can say that whenever that any gas or you can say more vapor from the liquid phase tries to condensate where the partial pressure will be equal to vapor pressure, the respective temperature will be called as dew point temperature. And at that condition the saturated vapor will have that partial pressure as that here Pi will be equal to what is that, if you know that total system pressure and components of that component A in that vapor phase, then you can calculate what will be the partial pressure, and then partial pressure will be equal to their vapor pressure of that particular components. So, when the partial pressure of this vapor in the gas phase is less than the vapor pressure, that is Pi less than Piv here as per notation, then the vapor phase is referred to a partially saturated vapor, or you can say that it will be superheated vapor, and then you can say that Pi will be less than Piv. Now, superheated vapor cannot condense unless that increased system pressure such that Raoult's law applies, and also decrease the system temperature to the dew point temperature there. So, these are the conditions there to the superheated vapor which may not be condensate at this condition. Now, let us do an example here. Let us say that a stream of air exiting a condenser at a temperature of 87 degrees Celsius and a pressure of 1.5 bar contains 25 mole % of water. Now, in this case you have to calculate what should be the dew point of the air. Now, in this case you have to first calculate the partial pressure of the water in the air that is entering to the condenser, and it can be calculated as that by that either by Raoult's law or by that simply that Dalton's law, that will be equal to partial pressure will be equal to that mole fraction of that components into its total pressure, then it will be coming as here 0.375 bar. Now, if the equilibrium between the two phases exists, the partial pressure of that water must be equal to the vapor pressure at that dew point. Now, this can be written as here partial pressure will be equal to vapor pressure. Now, using that steam table, the dew point temperature at that particular condition of that equality of that partial pressure to its vapor pressure at a particular temperature and pressure, that temperature will be as 74.66 degrees Celsius, that you can get it from the steam table, and pressure will be as 0.375 bar. So, we can say that simply here the dew point will be that temperature when this moisture partial pressure in the air will be exactly equal to the vapor pressure of that moisture in the air. What is that relative saturation and relative humidity? That is also important. In this case, relative saturation and relative humidity can be defined as what should be the partial pressure of the moisture in the air and what should be the vapor pressure of the moisture in the air at that particular temperature. The ratio will be regarded as relative saturation, or it is sometimes called relative humidity. And also you can say that if you apply the ideal gas law, the relative saturation or relative humidity can be defined as here you can say that what is the ratio of partial pressure to the total pressure. It will be regarded as simply that mole fraction of that components in the vapor, or you can see in the air here in itself for the humidity consideration, or in a systems of gas liquid mixture there. So, relative saturation to be defined as Pi by P divided by again the ratio of that vapor pressure to the total pressure. So, here basically the ratio of partial pressure to the total pressure to the vapor pressure to the total pressure. So, in this way you can write it. Seems here you can say that moles ratio is equal to pressure ratio is equal to volume ratio. So, we can represent it as volume ratio also here like this, and also you can represent it as that moles ratio here, and from that moles ratio if you multiply it by molecular weight, then you can represent it as mass ratio at that particular saturation condition. Now, from this principle you can say that if suppose relative humidity or relative saturation it is coming 0%, that means the air will be totally dry, whereas 100% relative humidity means that air will be saturated with moisture there. Another representation of that saturation called that molar saturation and also humidity respectively is called molar humidity. Molar saturation or molar humidity is defined as similarly by that mole ratio here, and also it is sometimes reported as a fraction or a suppose a percent here. Sometimes some books they are using as humidity representation like this, and also sometimes if the system consisted of water specifies I and air, then I free gas refers to the bone dry air for representation of this molar saturation or molar humidity. Now, what is the absolute saturation or absolute humidity? That is also defined as like here given in this equation here. So, this is basically the ratio of moles of that component I to the moles of its in the free gas there in actual condition, and also that ratio will be in the saturated condition, how it will be there, and based on that actual and saturation condition, if you make it ratio, then it will be called as absolute saturation or absolute humidity, and it is defined as by this equation. Now, in this case you have to remember that if suppose absolute saturation is less than relative saturation, then we can say that Pi, that means partial pressure will not be equals to that vapor pressure, but this will come only when then if this partial pressure is that changing or deviated from the vapor pressure. So, this absolute pressure will be then defined in terms of relative saturation and also the ratio of that vapor pressure to the partial pressure deviated from the total pressure. So, in this case of course that this absolute pressure will be less than saturated pressure. Now, another important point is dry bulb temperature in the gas liquid equilibrium condition. In this case the dry bulb temperature usually referred to as air temperature, that will indicate by a thermometer not affected by the moisture of the air, and dry bulb temperature it is denoted by TdB generally, and it can be measured using a normal thermometer freely exposed to the air, but shielded from radiation and moisture. Whereas wet bulb temperature is the temperature of adiabatic saturation. This is the temperature that is indicated by a moistened thermometer bulb exposed to the air flow, and the rate of evaporation from the wet bandage on a bulb depends on the humidity of the air, and the evaporation is reduced when the air contains more water vapor, and the wet bulb temperature always lower than the dry bulb temperature, and you have to remember that it will be identical with the 100% relative humidity there if the air is at the saturation condition. Now, dew point we have already discussed that what is the dew point temperature. It is basically the temperature at which water vapor starts to condensate out of the air, that is the temperature at which that air becomes completely saturated, and above this temperature the moisture will stay in the air, and if the dew point temperature is close to the dry air temperature, then the relative humidity will be high, whereas if the dew point is well below the dry air temperature, you can see that relative humidity will be low. Now, here one psychometric chart is given to calculate that humidity chart, and also what is that different components, what is the dry bulb temperature, what is the dew point temperature, how that enthalpy at saturation condition can be calculated, what should be the wet bulb or saturation temperature, how to calculate that absolute moisture content, and also what should be the humid volume there, how it is defined, and also there are other properties like what should be the enthalpy deviation, what is the relative humidity, how to calculate. So, I will discuss these things in the next lecture, how to use that psychometric chart to calculate the relative humidity and also dew point temperature, dry bulb temperature, enthalpy, even that what is the humid volume and also relative saturation, absolute moisture content in the air based on which. So, we will discuss more about that this humidity and condensation, and also what is that even saturation problem, condensation problem, evaporation problem. We will discuss more about that in the next lecture. So, thank you for your attention for this lecture.